Okay, for chapter 1, we are going to look for definition for chemistry. What is chemistry? Is the study of matter and the changes that the matter undergoes. So as the beginning of the chemistry, we are going to learn about some terms and the new terminologies. So one definitions for chemistry. Then when we say a study of the matter, what is the matter? Matter is anything that occupies space and has mass. Sometimes in everyday life, we use matter and substance and chemicals and compound interchangeably. But when you take a chemistry class, you want to make sure to know the definition for each one of them, like specifically, and one falls under another group or another class. So when you say like a substance which is the form of a matter. So when you talk about a substance, it has definite composition or distinct property. So we're talking about like substance. Matter can be classified. It can be classified to like pure substances or mixtures. So when you say substances, something that has definite composition, when you talk about water, if you have pure water, any molecule or any part of the water sample that you take is composed of H2O. Or when you have ammonia, it's like NH3. If you have gold, like a AU, or oxygen, like a O2. So these are all pure substances. And then you could have like a mixture. What is a mixture? A mixture is a combination of two or more pure substances. So when you're talking about mixture, you could have two pure substances. Let's say you have like soft drink, it's or carbonated drink is a mixture of CO2, carbon dioxide, and some sugar, some water, and other additives. When you talk about mixtures, mixtures is different from pure substances, because mixture is a combination of two or more substances, and the composition, it can vary. So let's say you have like salt water, you could have like 10% sodium chloride solution, aqueous solution. This means sodium chloride, which is a table salt, has dissolved in water. You could also have like 15% NaCl aqueous solution. Both of them are homogeneous mixture. What does homogeneous mixture? It means that the composition of the mixture is the same throughout. That means if you have a container of like salt water, you take a spoon of it in this area or from this area or any other area, it's going to taste the same and it looks the same. Homogeneous mixture, the other name for it is solution. So it's evenly distributed throughout. So, and you don't see the components. Like if you have salt water, you do not see the salt and water separately. Versus heterogeneous mixture, when you talk about heterogeneous mixture, the composition is not uniform. An example of that is going to be like sand and water. You have pieces of rock in water. That's like heterogeneous mixture. The examples that was used in the assignment, it was like a chicken noodle soup. What is it? Chicken noodle soup. If you take your first spoon of the chicken noodle soup and the second spoon, is a guarantee that it's going to be exactly the same? Maybe or maybe not, right? So if it's not the same, that means is heterogeneous mixture. At the same time, you can see the component. You could see the chicken. You could see the noodles. You could see other stuff that was mixed with the or added based on the recipe, you could see them. You could see some other vegetables. You might see other whatever is added, or if you have like a garden salad, it's going to be a heterogeneous mixture because you could see the lettuce, you could see tomato, you could see other things that was added to the salad. The difference between mixtures and the pure substances is that pure substances are already pure. You cannot separate them. You cannot bring it to like simpler compound or simpler substance. But when you have mixtures, like if you have mixtures of iron with, let's say, salt, or if you have iron and sulfur, if it's a magnet, you can separate the iron. If you have salt water, you can use distillation. Salt water is salt dissolved in water. You could use distillation. The water would evaporate, changes to water vapor, then you condense it. This is a condenser that can lower the temperature of the water vapor. Is going to then change to liquid, and you collect the water here. The salt would stay in the boiling flask. So the component of a mixture can be separated and into its pure components. So components of a mixture can be separated by physical means. These are like some filtration, decanting, distillation. These are physical means. Like if you have mixture of sand and water, you can do simply filtration. You can separate it by filter paper. Let me know if you have any questions. You can use the chat option to write or type your questions. I will make sure to answer it as I'm presenting. When it comes to pure substances could be elements or compounds. What is element? Anything that you see from in the periodic table, it's called element. And element cannot be separated into simpler substance by any chemical means. Example, let's say you have sodium, and sodium atom has 11 protons. It has 11 electrons. This is for a neutral sodium, 11 proton, 11 electron. And if it's a sodium 23, it has 12 neutrons. These are subatomic particles for sodium. Any atom that has 11 proton is called sodium. Okay, if it has 11 proton, it's called sodium. Now, can you divide this into half and make like a can you make like a 5 proton and then 6 proton? Can you divide it? If you divide it, well, you can divide it. It's not going to be easy. It's going to be very hard to divide it. But if you divide it, this is not sodium anymore. It's going to be boron, and 6 proton is going to be carbon. Is not sodium anymore. So if it's element, you cannot break down. Even by chemical means, you cannot break down. When it comes to compound, however, compound is a combination of 2 or more elements. Okay, like compound of water is made of H2O, and the H2O is made of hydrogen and oxygen. If you do electrolysis, you basically can separate hydrogen from oxygen. So water, a compound, by chemical means can be separated to simpler substances, to its elements, but is not going to be called that compound anymore. Is not going to be called water anymore. It's going to be called hydrogen gas and oxygen gas if you separate it. So it's going to be based on a chemical reaction. A summary of classification of a matter is presented in this diagram. So you start with the matter. Matter can be either pure substances or mixtures. Pure substances would be either elements or compounds. Compounds are more complicated than elements. Elements cannot be broken down to smaller units or smaller substances that still represents that element, because then you have to basically change the nucleus of the atom. You cannot, then the atom would change, is not the same. But compounds can change to elements. When it comes to mixtures, mixtures is a combination of two or more different pure substances. It's a different story. You can actually separate the component of a heterogeneous mixture and homogeneous mixture, both of them. In homogeneous mixture, you don't see the component, but you find a way to separate them. You will learn in the lab and in the, how to separate them. And when it comes heterogeneous, it's easier to separate the components because you could see them, you could see where they are, what they are. You could use like separator funnel, you can use decanting, you can use filtration, you could use distillation, and distillation is used more often for the homogeneous mixture. But those are some physical means that you can actually use for separation of components of a mixture. Perfect. Okay. The other terminology and definitions that we want to review and know about is the state of the matter, or the states of the matter, the ones that are more popular. We are using solid, liquid, and gas. We are not routinely study about plasma or like super critical fluid and other states that are not very routine. Those are like very specific, and it could be mentioned. So I just want to make sure that I know it's not only these three, but these are the ones that are studied in this book or in this course. How do you change solid to liquid to gas, and what is the difference between them? For solid, we have definite shape, or a solid has definite shape and definite volume. The blocks, or the building blocks of the solid, they are in rigid position. There is no space between them, or minimum amount of space between them. There's no space between them. When it comes to liquid, or how do you change this to liquid, you have to heat up this sample. When you heat solid, you're basically giving energy to this molecule. That energy is going to be saved as kinetic energy. And when the energy is enough for this molecule to be able to move around and slide over one another, is going to create some space between the molecules, then you have a liquid. It's going to change to liquid. Liquid has definite volume, but it doesn't have definite shape. If you have the liquid, you pour into a glass, it takes the shape of a glass. You change it to a flask, you pour into a flask, it takes the shape of a flask. You take it to a bottle, it would take the shape of the bottle. So it doesn't have a definite shape. Why doesn't it have definite shape? Because these molecules are moving around, and they are going to basically, based on the space that you have between the molecules, it allows these molecules to be flexible in terms of the shape, and is going to take the shape of the container. Now, how can we prove there's a space between the molecules? What happens if you have 1 cup of water and you just measure exactly, you have 100 milliliter of water, H2O, and then you get like another cup and you fill up to 100 mark here, 100 milliliter mark, and you add sugar. So what happens if you pour the sugar into 100 ml of water? The volume might increase to 102 or 105 or 110, but definitely is not going to be 200. So if you're adding a solid into this liquid, the molecules of the solid would reside or would go into spaces between the molecules. That's why you don't see a significant change in volume. So that's like a proof scientifically or experimentally that there's a space between the molecules of liquid, and they're moving around, they're flexible. Between the gas molecules, there's huge amount of space, lots of space. Gas molecules, they are highly energetic particles, and they constantly move. They constantly move in the don't know where is the okay video. Okay, they're constantly moving, so they would move into a straight line, constant motion, straight line. When they hit the wall, they would go back, or they would bounce back, or hit another molecule, would bounce back, and moves straight again in different direction. But they're constantly moving. In order for gas molecules to constantly move, they must have a lot of energy. So you have to actually apply more heat in order for this liquid to change to gas. Gas doesn't have a specific definite shape or definite volume, and it can take the shape and the volume of a container because the molecules are moving constantly, and there's lots of space between them. It gives different properties to the gas molecules. We learn about that in Unit 6 when we talk about compressibility and then transparency and other properties of the gas. But just to phase changes, for solid go to liquid to gas, you need increase the temperature, and vice versa. To go from gas to liquid, you have to lower the temperature and then freeze it to go to solid. Other terminologies, you have like 4 definitions: physical change, chemical change, physical property, and chemical property. What are those? The physical change is the change that does not change the composition or identity of a substance. One of those examples is like a phase change. If you have ice, when it changes to water, you still have H2O. Composition did not change. The other characteristic for physical change is that it's reversible. So if you have water, you cool down, it goes back to ice. Versus chemical change, in the chemical change, composition of the compound is changing. When hydrogen gas burns in oxygen, it forms water. The water molecule does not look like the hydrogen gas or oxygen gas because it's liquid, and your hydrogen gas, oxygen gas, they look different from the water. The composition of the compound is changing. It's not reversible because you cannot just change water to gas, a hydrogen gas and oxygen gas, unless you do a chemical process. So by physical means, you cannot change water to hydrogen or oxygen gas. The other 2 definitions that is not here, but I want to make sure you know about, is the physical property and chemical property. What is physical property? Physical property, those are property of a substance that you can actually measure or find out or determine using your senses, or you can measure it in the lab by simple physical measurements. Like boiling point. You can measure the boiling point without changing composition of the compound. That's a physical property. Color. You watch, you look, you see the color. Shape, mass, volume. Those are physical properties. Okay. Density is a physical property. How do you call density a physical property? Because in order to calculate density, you need mass, you need volume, and both of them you can measure without changing property or changing composition of the compound. So it is going to, is a derived unit or is a derived property is a calculated property, is not like measured directly, but is a physical property. So density, boiling point, melting point, color, shape, shininess, is it shiny or is not shiny, or conductivity. Those are physical properties. Now, what is chemical property? Chemical property can be measured by making a compound go through a chemical reaction. Let's say you have solid sodium and you have chlorine gas, Cl2 gas. When you combine these two, is going to give you NaCl solid. If we balance this equation, 2 sodium with 1 Cl2 is going to give 2 NaCl. Now, chemical property for sodium is that is able to react with chlorine and give sodium chloride. That's chemical property. You can only determine in a chemical reaction. And by the time you determine that, composition has changed. On the reactant side, you have a shiny metal. On the product side, you have like a white powder. Sodium is combined with something else already. So in order to determine chemical property, the composition of the compound is going to change. So it's like ability for substance to go through chemical reaction. That is chemical property. So when we talk about like physical properties and chemical properties, for the physical properties, you can do some measurements, and in the measurement you use units, okay, and you use measuring device. Some physical properties that can be measured is like mass. Definition for mass. What is mass? Is the measure of quantity of matter. So if you say 0.5 kilogram object versus 1 kilogram object, the 1 kilogram object has higher quantity of matter. And the unit used for mass, the SI unit used for mass is kilogram. What is SI? SI is an abbreviation for International Standard of the Units. There's like agreement among like internationally for the science between the scientists that they have like 7 base units that everyone agrees to use these units. Like for mass would be kilogram, and I do have a slide that I will share with you with all 7 of them in one place. So you have your the definition for mass, quantity of the matter. Weight is the gravitational force on the object. Mass does not change based on location, but weight based on the location, it can change. So if you measure the weight at the surface of the Earth or moon, is going to be a different value. So for something that is 1 kilogram bar on the Earth, when you move it to moon, is going to be 0.1, because the gravitational force on the moon is lower, is a fraction, is like 1/10 of it compared to the Earth. But when you measure it, you're not changing the composition of the compound, so that's why it's classified as physical property also. The SI unit, or the SI base unit that I was talking about, for the length, meter is used. The subunit of that is going to be centimeter, millimeter, kilometer. For mass, kilogram. So these are the SI units. You should be familiar with them. We use all of them in chemistry except for the current and the luminous intensity. These 2 are not very popular, but everything else is used every day in chemistry. So when we talk about like SI units and the subunits, or with the prefixes of these base units, And then we talk about other units that are used for measuring, like length. Can you name other units that are used for the length other than meter, centimeter?
Millimeter.
Okay, millimeter. What else? Feet, yards. So if we have different units for measurement of the length, we need to learn about conversion, and we should be able to convert from one unit to another unit using conversion factors. So these are the SI based unit, but these are not the only units used for these measurements. The prefixes, I remember about 20 years ago when I was teaching, or 25 years ago when I was teaching chemistry at the college, I said, just know about kilo, deci, centi, and milli, you should be fine. Mega, maybe. And then now, with the nanoparticles technology, so nanometer is popular. So for your generation, you need to know about the nano. If you're using computer with this hard drive, you should know about tera, and you should know about giga, because you're using the gigabyte and megabyte. These are like very, very popular now. It wasn't that they were not that popular 25 years ago when I was teaching. When I didn't start teaching then. I think I've been teaching more than that. Been teaching for 28 years, 1992. How many years? 29. But these days everything is like very popular, all these prefixes. So most of them already. What is SI derived units? SI derived units is like you are using the base unit from SI, which was meter, and then you are going to use the base unit and calculate the derived unit for volume. When you measure the volume, you are going to measure the height, measure the width, and measure the depth, and multiply the three of them together. If you are going 1 meter times 1 meter times 1 meter, you cannot say 1 meter, because that's not 1 meter anymore. Any operation that happens with the number, it must happen with the unit as well. So meter times meter is going to be the meter square, and then meter square times meter is going to be cubic meter. So cubic meter, which is a unit for measuring volume, is derived SI unit, or SI derived units. So a cubic meter is for a cube that has 1 meter on each side. Okay, and cubic decimeter, cubic decimeter is a cube that is 10 centimeter on each side. So 10 centimeter, 10 centimeter times 10 centimeter, that is going to be 1,000 cubic centimeter. 1,000 cubic centimeter equals to 1 liter. So 1 liter is 1,000 milliliter. 1,000 milliliter equals to 1,000 cubic centimeter. And as a result, this is something you need to know from now on. 1 milliliter equals 1 cubic centimeter. So you can always change it, or convert from one to the other, or just express it based on. For example, when you are measuring volume of an object, you measure, you fill up graduate cylinder if it goes to 50 milliliter, and then you drop your object in, and then this object is going to displace the water, and it's going to go, let's say, to 58.2, and this 58.2. The difference is going to be 8.2. 8.2, is this milliliter or is it cubic centimeter? On the graduate cylinder, I read it as the milliliter, but since 1 milliliter equals 1 cubic centimeter, when I want to express the volume of the solid, I would say that is 8.2 cubic centimeter, because I'm not using milliliter for solid. Numerical value is the same, but I have to express it in the right unit. Okay, other derived units are for like density. Density has also a SI derived unit. Definition for density is mass over volume. And the unit that is used for mass, if you're using gram for mass, then volume milliliter, the unit for density is going to be gram per milliliter. For liquids, okay, for liquids, we use gram per milliliter for density. For solid, we use gram per cubic centimeter. And then for gas, is going to be for gas, maybe I do this instead. Okay, for gas is going to be gram per liter. Now, when we say density of H2O equals 1 gram per milliliter, what does it actually mean? What it means that, maybe you want to respond to this. What does it actually mean? Density is 1 gram per milliliter. What it means? What does it mean? Density of 1 gram per milliliter for water. It means 1 milliliter of H2O equals 1 gram, right? 1 milliliter weighs 1 gram. 10 milliliter would be 10 gram. So that is the meaning of the density. When you have the density of 1 gram per milliliter, that means 1 milliliter of that liquid is 1 gram. And why do we use the gram per liter for gas? Is that for gas, why do we use that gram per liter? Because gas doesn't weigh much. And if you take 1 milliliter, the number is going to be very small. And scientists, they don't like to work with very small numbers. They don't like to have this like multiple decimal places or many zeros before the number. So they use a more workable, they like to work with more workable numbers or for the convenience. So instead of measuring the mass for 1 milliliter of the gas, which is tiny, they would use 1 liter of gas and measure the mass for that 1 liter. Okay, now talk about density. What is the application? Why do we calculate density? Density is a physical property. So you can identify a compound based on physical property. Density of water is 1 gram per milliliter, and density for alcohol or ethanol is like 0.78 gram per milliliter. This is for ethanol. Now, if you have a bottle that we don't know is water or is ethanol, you can smell it. You can also be more scientific about it and measure the density. If you measure this one density is measured 1 gram per milliliter, then definitely is water. Or if the density is 0.78, then definitely that is going to be ethanol. Let's say there's a piece of mahogany and they don't know if that piece of mahogany is coming from Honduras or if it's coming from Spain. Apparently they have different prices and there's argument. A scientist would come in and measure the density of the wood. And if it does match with the mahogany from Honduras, then it says this is from Honduras, it's not from Spain, and vice versa. So one is for identification. Second, if you have the density, you have the volume, you can measure the mass. If you have the mass and volume, you can measure density. And any two you have, you can measure the other one. So it's just equation with 3 variables: density, mass, volume. If you have the density, like you have the density of this metal here, and you have the volume, you can measure the mass, and vice versa. Another measurement here is temperature. Temperature is, we have 3 different units for temperature. They're all set up based on a freezing point and boiling point of water. Freezing point of water is recorded as 0 degrees Celsius, and they were like different scientists who came up with these devices, and they actually designed this device. And like Celsius, put the 100 degrees Celsius boiling point for water and 0 degrees Celsius for freezing point of water. And as you heat up or as it gets hot, the thermometer bulb, the liquid expands and it goes up. And it reaches to this level that is at the boiling point of water. If this space is divided to 100, then you find the magnitude for 1 unit or 1 degree Celsius. For Kelvin, freezing point was called 273, and the boiling point is 373. This is also 100 units. So if it's 100 units, then the magnitude for Celsius and Kelvin is going to be equal. The only difference, the numerical value is different because you're talking about Kelvin, absolute temperature. 273 is the freezing point of water. 0 Kelvin is the absolute 0. That means there is no movement after that. So that's the lowest possible temperature. It even has not been reached yet. They can create that temperature in the lab very close to it, but they haven't reached the 0 Kelvin yet. But it's known to be the absolute 0. Life is not possible at that point, even for gas molecules. So anyway, the Fahrenheit 32 to 212, this is 180. So if you want to find the unit here, you have to divide by 180. So you divide the same distance by 100 or 180. These units are different. So when you're converting, you have to keep that in mind, that Fahrenheit has a smaller unit compared to Celsius. If you want to go from Celsius to Kelvin, simply you just add 273 because these magnitudes are the same. But if you want to go from Kelvin to Celsius, you subtract 273. For Fahrenheit to, if you have Celsius and you want to go to Fahrenheit, you have to consider this ratio of 180 over 100, okay? Which if you simplify it, is going to be 18 over 10 or 9 over 5, or you might even see that 1.8, that's 9 divided by 5. So you multiply the Celsius by 1.8 or 9 over 5, and then you add 32 because 0 Celsius is 32. So you have to look for the ratio and also the base unit. Basically, you have to memorize this formula, but you are going from smaller number to larger number. You see 100 degrees Celsius is 212 Fahrenheit. So a smaller number to larger number. First, you do multiplication and you multiply by a ratio that is greater than 1. It's kind of makes sense and it helps you to understand. And then you add the 32. If it was reverse, for the reverse calculation, going from Fahrenheit to Celsius, you subtract 32, okay? You subtract 32 first, and then multiply by 5 over 9 and not 9 over 5. So if you have the Fahrenheit and you want to go to Celsius, you subtract first 32 and then multiply by 5 over 9. The order of the operation and how the formula looks like, you might forget it, but if you do calculation, going from Fahrenheit to Celsius, you should come up with smaller number. That's like a checkpoint for you. That's how you check your answer. Scientific notation. Remember I said that you are a scientist. They like to work with workable numbers. They don't want to deal with all these zeros, decimal places, or these zeros here. So they express the number in scientific notation. Scientific notation, A times 10 to the power of B. This is the power or exponent, and A is called coefficient. In this case, N is called coefficient, and this is the power. Power could be positive or negative. If it's negative, that means the number was less than 1. And if it's negative, the number is less than 1. If it's positive, that means your number was greater than 10. The value for N, for a standard N or A, for the coefficient, for standard scientific notation, it should be between 1 and 10. It doesn't have to be between 1 and 10 if you're not talking about standard scientific notation. Often, they're just using standard scientific notation. That's why this slide here, it doesn't say that for standard scientific notation. So scientific notation, A could be any number, but for standard scientific notation, that number should be between 1 and 10.
Yeah, bye, Professor.
Yes.
Goodbye. I gotta leave.
Okay.
All right, thank you. See you on Thursday.
Thanks.
Goodbye, Professor. Have a good one.
Your question about how did we come up with this equation, going from Celsius to Fahrenheit, rearrange it to go to Fahrenheit to Celsius, is just rearranging of the formula. You can learn these formulas separately. Just say, if you want to go from Celsius to Fahrenheit, you use equation 1. And if you want to go from Fahrenheit to Celsius, you would use equation 2.
Okay, so where did the fraction come from?
These fractions. This
Yes.
fraction, it's showing the ratio between the magnitude of degree Celsius and degree Fahrenheit. The magnitude for the degree Celsius and degree Fahrenheit, if we go back to slide before, you see for the for Fahrenheit, we have 180 units here, but it's the same distance. Okay, it's the same distance, but it's like 180. For Celsius, is 100 units, same distance. It's like you have $100 and you divide that between 100 people, each one would get $1, right? But if you divide this by if you divide the $100 by 180, then each person is going to get less than $1. So these numbers are going to be like very small. If you look at a couple examples, it might also help you, like room temperature. Room temperature is 25 degrees Celsius. But you don't put your air conditioner in Florida at 25, because 25, the unit that is in the thermostat is actually Fahrenheit. It shows Fahrenheit, not Celsius. So instead of that, you put like around 77, right? You put like 77, that's your room temperature, or is known as the room temperature. But if you go from like 77 to 98, what's the difference here? 98 to 77, that's like 22, right? 22.5, 2.6, 22.6. But that is 37 minus 25, that's 12, right? 12 increase in Celsius, that translates to 22.5 increase in Fahrenheit. So there is no like simply adding 32. Because if you just add 32, is not going to convert from Celsius to Fahrenheit. You have to say, what is that number in Celsius? You multiply by the ratio of 180 over 100. That is the ratio. 180 over 100 can be simplified to 9 over 5. And that's where the fraction is coming from.
Oh, okay.
That's what you're welcome. Yes, I'm glad you asked the question. So that's where the fraction is coming. And when you are going from Fahrenheit to Celsius, because the number should get smaller, then you are going to multiply by a different ratio, and that is a 5/9, because you're trying to reduce this number. It should go a lower magnitude. The value is going to be lower, but it might help you to memorize these two equations like separately. Equation 1 going from Celsius to Fahrenheit, equation 2 going from Fahrenheit to Celsius. And then for Kelvin and Celsius, simply you either add or subtract 273, depends on which way you're going. And there is no conversion between Kelvin and Fahrenheit. If you want to go from Kelvin to Fahrenheit, first you have to go to Celsius and then convert to Fahrenheit.
Okay, thank you.
You're welcome. Okay, when you have the numbers in scientific notation, you can then do some, scientific notation. You can change it to decimal number, or you have decimal number, you can change it to scientific notation. If the number is greater than 10, you move decimal place to the left until you have only one digit to the left of decimal place. And then you count how many times did you move that number. So since you moved like 2 times to get to one digit to the left of the decimal, you move 2 times. That 2, it goes as exponent for 10. If the number is less than 1, so you are going to get the exponent of exponent is going to be negative, and the decimal place is going to be moved right. And you look for how many decimal places you have moved until you get one digit to the left of the decimal place. So you have decimal place is going to stop right here. You're going to have 7.72. Then you count how many places you have moved. 1, 2, 3, 4, 5, 6. So the number is going to be 6 places, but since you moved to the right, is going to be -6. And this number was less than 1, 7.72 times 10 to -6. The value for coefficient is going to be between 1 and 10. You have the value for coefficient. Any number that appears in the coefficient, it's called is a significant number. Now, when you have numbers expressed with scientific notation, when you try to add or subtract, they must have same exponents. So if they don't have same exponents, you have to convert one of the numbers in order to get same exponent for both. So you have a 3 and 4 here. You're going to change the 3.9, 10 to 3. You want to change this to 4. So you're moving decimal place to left to increase this number to 4. So you have 0.39 now times 10 to 4. This is what I was talking about. This is a standard scientific notation, but it's not standard scientific notation. But for the purpose of addition, you have to have same exponent. So you change your coefficient. Now, you would then add the the two coefficients, you add them and use one of the exponents, okay? Use one of the exponents. If you multiply or divide numbers expressed in scientific notation, the rule is different. So when you multiply, you just multiply the coefficients. So you have a coefficient, then you have your exponents. So you multiply the coefficient and you add the exponents. You are going to express with a proper number of significant figures. When you are multiplying, you count the number of significant figures. Like here, you have two significant figures, final answer should be two significant figures. You find 28 times 10 to negative 2. This is scientific notation, but it's not standard scientific notation. To make it standard, there is an assumed decimal place after 8, because you don't see decimal place, so it's going to be assumed after 8. You're going to move that by one space to the left. So since you're going to move it to the left, 2.8, you add 1 to negative 2. So it's going to be negative 2 plus 1, that equals minus 1. You get the new exponent. When you divide, what happens again, you have coefficient, and you have exponent, exponent. You are going to divide the coefficients, okay? You are going to divide the coefficients, and then you're going to subtract the exponents. 4 minus 9 is going to be negative 5, and 8.5 divided by 5 is going to be 1.7. Significant figures. There are some rules to count significant figures. When you take your experiment 1, it's going to, in the lab, is going to help you understanding of the significant figures, the meaning of the significant figures also. So we're just going to practice with the rules. If you have non-zero digits, 1, 2, 3, that's 3 significant figures, non-zero. If you have a 0 between 2 non-zero digits, that's also significant. So we have 3 significant figures. If we have scientific notation 5.00 times 10 to negative 5, okay, that's any number that appears in the coefficient is significant. Since there are 3 of them, so that's going to be 3 significant figures. When you have 0 and is not, okay, and is not the scientific notation, if you have 0, let's say you have placeholders like 0.0052, okay, and you see the decimal point here. The zeros to the left of a non-zero digit are not significant, so you only have 2 significant figures here. If you have 0 to the right of a non-zero digit, and you have to look for decimal place. Do you see decimal place? If you don't see decimal place, these are just again, as a placeholders. It shows the magnitude of the number and is not going to be significant. So you only have 2. But if you have like 5.200, you have zeros to the right of a non-zero digit, and you also see the decimal place. If you see the decimal place, these zeros become significant. So this is going to give you 4 significant figures. So if you have like a number 0.00580, these zeros are not significant because they are to the left of a non-zero digit, but this 0 is significant because you can see the decimal place. So it's going to be 3 significant figures. Some examples here, when you do like measurement, which shows the unit that, or the number of significant figures that you express your number. It shows how accurate is your measurement, or how expensive was the device that you use for measuring as a measuring device. So 24 milliliter, that's 2 significant figures. That's easy. These zeros are between non-zeros, so you get 4 significant figures. This is not significant, but this number 0 is significant, so you have 3 significant figures. For the coefficient, all the numbers are significant. You only have 2 that's significant. For a number 0 to the right of non-zero, because you don't see the decimal place, this is not going to be significant, so you only have 2 significant figures. When you do addition or subtraction, you count decimal places. And the number, the final answer cannot have more decimal place than any given number. So this given number, you have 1 decimal place. This given number, you have 3 decimal place. I underline decimal places. I use, for significant figures, I use like a parenthesis, just me. So 1 decimal place, 3 decimal place, the final answer cannot have 3 decimal place because one of your number has only 1 decimal place. So what you do, you're going to count 1 decimal place right here, and 3 is the first digit that you don't want it. Since it's less than 5, you just drop it and you don't have to worry about it because it's after decimal place. So you just report as 90.4. When it comes to this is subtraction, the rule is the same. You have 2 decimal place for this number, you have 4 decimal place. Your final answer cannot have more than 2 decimal places. So you count 1 decimal place, 2 decimal place right there, and you have to drop the 6 and 7. You don't have to be worried about 7. So start with the first number that you don't want it. Since it's greater than 5, sorry, you add 1 to the previous digit, and it's going to be 0.79 with 2 decimal places. When you multiply or divide, you count significant figures. So you're going to count the significant figures. We have 3 significant figures here. We have 5 significant figures. And for this next number, we are only allowed to keep 3 significant figures. We start from the first number on the left, 1, 2, 3. So we keep these 3. The first number we don't want to keep is 3. So we just drop and we don't have to worry about it. Okay, because it's after decimal place. You don't have to even replace it with non-zero. When you have decimal place, you just drop the number that is less than 5. For the next example, with division, you divide the 2 numbers. You have 2 significant figures. You have 5 significant figures. Your final answer cannot have more than 2 significant figures. So you're going to start counting from the first non-zero digit, 1, 2. You're going to keep these 2, and then you have to drop the rest. You look at the first digit after that you don't want to keep is greater than 5, so you add 1 to previous one, and you report your number with 2 significant figures. This is not a significant figure, it's just a placeholder. Exact number and measured number, when it comes to like exact numbers, those are by counting. So you have like in this case you have 3 is an exact number because you have 3 measurements. So you don't have to worry about significant figures that you have for the exact number. This is just the 3 numbers. Exact numbers can have unlimited significant figures. So when you are looking for significant figures, you only consider the measured numbers. So in this case, you're adding 2 decimal place, 2 decimal place, 2 decimal place. Your final answer should have 2 decimal place. You don't have to say, okay, I'm dividing by 3, so I have to have 1 significant figures, because this is exact number and it can have unlimited significant figures. You need 3, okay, it's going to be 3.00. So you can keep this with that number, okay, with the number of significant figures that you are looking at your measured numbers. Do not include definition. Like let's say if you have 1 milliliter, 1 meter equals 100 centimeters. And you want to go from meter to centimeter or centimeter to meter, you are using conversion factor. Because this is definition, you don't count the significant figures of 1 meter or the 100 centimeter. So you just use the conversion factor. Let's say you have 5.8 meter and you want to know how many centimeters there. You would say 100 centimeter over 1 meter. So if you were going to use significant figures for the 100 and for the 1, you're not going to get proper answer. But you just say, okay, I have 2 significant figures here. On the product, I have 2 significant figures. So you would say 580 centimeter. And since you have 2 significant figures, you are fine. You don't have to make any changes. Other definitions is definition for accuracy and precision. Accuracy meaning that how close are measured number to the target value or true value. And that's the case here. If the target value is right here, your measurements are very close to target value or true value. So this data is accurate data. And if your data is accurate, that means they're also precise, because if you look at the definition for precision, it means that how close they are to each other. If they're all close to the true value, they must be close to each other also. So if it's accurate, it's going to be precise. But if it's precise, it doesn't have to be accurate, because precision meaning that they're close to one another, but doesn't mean that they are close to true value. So in this second diagram, you have precise, but not accurate. But the third diagram is not close, the measurements are not close to the true value, and they're not close to one another, so not accurate and not precise. If you get this type of data that is precise but is not accurate, that means there is like a problem with your instrument. Like if your measuring device, like your thermometer records, every time you make measurement, it records, it's broken, and it records 5 degrees lower, then your numbers, even though they are very, you do everything right, but your numbers are going to be 5 degrees lower than what it should be. But your measurements were correct because the way you performed the experiment were correct, because you're getting like precise numbers. So it's just more information here. Okay, when you are doing calculation, a factor label or dimensional analysis, okay? Dimensional analysis, so you are going to convert from one unit to another unit. First of all, you need to know what is the equality. The equality, like in this example, you have liters and you want to go to milliliter. The equation 1 liter equals 1000 milliliter is the equality. So that's the unit conversion. Every 1 liter equals 1000 milliliter. From that, you can extract 2 conversion factors, A and B. A would be 1 liter over 1000 milliliter, and B is 1000 milliliter over 1 liter. So these are 2 possible conversion factors. Which one are you going to use? Well, what is given to me is liter, but I want to cancel the liter. I want to go to milliliter. So I'm going to start with 1.63 liter. And I have to choose between A and B. Which one should I choose? Because I want to cancel liter, I have to use B. And I have to use B because I want to cancel the liter. So the liter has to be in denominator. So I'm canceling the liter. I carry out the unit. Through the calculation, I have to write the units and cancel the unit, because liter divide by liter, you're going to cancel the unit. And then you end up with the wanted unit. Your wanted unit is milliliter. Now, how many significant figures you have in the given number, that's the number of significant figures you should keep for the final answer. So you have 3 significant figures, we are fine. This example, it shows what would happen instead of equation conversion factor B if you use A by mistake. You see the unit will not cancel. You're going to get like a unit as a result that it doesn't make sense. Now, another example, when you have like a derived unit and you want to convert to another derived unit, so you have a meter per second, you want to go for a mile per hour. What you do in this case, you just take one step at a time. First, you convert meter to miles, and then convert second to hour. So you start with this number. You say you have 343 meter per second. You want to convert meter to mile. Now, meter to mile, you need to know the conversion factor or equality equation. 1 mile is 1609 meter. So if 1 mile is 1609 meter, then you have the same situation, 1 mile over 1609 meter. And that if we call this A, B is going to be 1609 meter over 1 mile. Now, which one are you going to use for the conversion? What you want to do? You want to cancel meter. So if you want to cancel meter, you have to use the conversion factor. That meter is denominator, and you can cancel it, and you cancel it. Up to here, you have changed meter to mile when you do this calculation. Now it's time for you to cancel second, and you want to cancel the second to hour, change to the hour. If you already know 1 hour equals 3,600 seconds, you can use this directly. You would say 3,600 second over 1 hour. Then you cancel the second. You see, second is at the bottom here, and the original given number. So when you are using conversion factor, second should be on top because you want to cancel the second. This may not be easy to remember, but this is really easy to remember. So you can break down to two conversions that they are easy to remember. So you go from second to minutes first. And in order to go from second to minutes, you basically have to multiply by 60 over 1, 60 seconds over 1 minute. And up to here, you have converted the second to, second, per second to per minute. But you want to go from per minute to per hour, you need to cancel the minute. So since minute is down, you have to use a conversion that the minute is on the numerator on top, so you can cancel. 60 minutes is over 1 hour, so you cancel the minutes, and then you end up with the mile per hour. So if it's a derived unit, it's a combination, there's no conversion factor that is going to convert in one step. You have to do multiple steps, and in the multiple steps, you convert one unit first and then the second unit.